Okay, welcome back to part 2 of the Unit 7 test review. I worked through parts 1 and 2 of this solution, okay? So I did all of this in part 1. Oh man, that's a lot of stuff. And now I'll do part 3. I just had to take a break last night. So, part 3 of this test review is have you mastered the material? So if you're going for an A, a high A, maybe 100, if that's your goal for the exam, you probably want to do this section, okay? Because these are the similar ideas, nothing really new here, but probably at a more difficult level. The difficulty level is increased to see if you really remember your stuff and can think creatively about these functions to do whatever, solve them or whatever. Okay, so let's start with number 14. Says sketch a graph for each function below, give the domain and range, identify the coordinates of the function's endpoint or inflection point, and state the function's end behavior. And it says, no, it's not necessary to find 3 points. The idea here is we are sketching an image of the graph, thinking a little bit abstractly about what it looks like using function transformations without really graphing it, right? Without using graph paper and plugging in points to figure stuff out. So like for letter A here, there's 3 things here. There's this 3, there's this 14, and there's this -5, right? Now, the 3 is a vertical stretch. The -14, because it's inside the radical, that's a shift right. And the -5 is a shift down. And those are my function transformations. So if I were to sketch just a quick picture of this graph, it might look like this. I'm going to create a little coordinate grid here. And it's shifted right and shifted down. So I'm just going to eyeball that. It's pretty far right and not that far down. So let's call that point 14, 5. And I know that it's vertically stretched. So if the original function looks like this, I know that a stretch function is going to go up a little bit higher like this. It's going to grow a little bit faster. Or rather, its height is going to be taller. I know it's not vertically reflected or anything like that, so it's going to look something like that. Yeah, that's good enough. Okay? And that's my square root curve. And you see, I've just sketched a picture of this. But using this picture, I've identified the endpoint. So I'll say the endpoint, because what you're doing is you're shifting the original endpoint, which was at 0, 0 right here. Right? You're shifting it from the origin, right 14 down 5. The endpoint is at 14, -5. Well, that should be negative here, huh? Boop. Let's make that 14, -5. Yeah. Okay. So that's my endpoint. It also says we want to give the domain and range of this function. And that's kind of the primary reason for sketching this picture. My domain is my x values. Notice it starts at x equals 14 and the curve goes right to infinity. So the domain is going to be 14 to infinity. The range, well, the lowest point on this graph is also at that endpoint, -5. So I'll say bracket -5 because it starts there and continues upwards towards infinity. Now, the last thing it says is finally state the function's end behavior. So end behavior, I guess I haven't talked a whole lot about this in class, at least not this year. Let me explain that a little bit here. I'll probably make another video talking about end behavior, but it's very simple. End behavior is how does the function trend towards its ends. So here's how we describe this. The ends of the function, we're going to look at the left end and the right end. And the way we do this is we say, as x approaches some value, then where does y go, right? So you can think of this as, we're going to describe both ends, as x goes to the right and as x goes to the left. And we're just going to think about, where is it going on the right and the left? Well, if x is going right, it's continuing on towards infinity. So I say, as x goes towards infinity, right, as I go to the right this way, where is y going? Well, y is going up. And it's not approaching any limit or, apex value or whatever, no maximum. So it's just going to continue towards infinity. And that's it. That's pretty much it. I'll also describe the other end, though. As x approaches, well, where is it going on the left? It's not going towards negative infinity because there's a hard stop at 14. The function does not progress past 14 in the negative or towards the left. So I'll say, as x approaches 14, where is y going? So think about reading the graph from the left, or I should say from the right, going left. So I start over here and I'm going right, or left. I can't speak. And as I go left, oh, it's going down, down, down to 5. So I say, as x approaches 14, y approaches -5. And that's it. That's pretty much all we write for end behavior. You're going to talk a lot more about end behavior in pre-cal and calculus. Not a major focus for us right now, but it's a good idea to introduce it now while we're taking algebra. Okay. Moving on to B. This one's a little tricky. This one is going to get you in pre-cal all the time because of the phase shift of sine functions. So recall that our function transformations are a times f of b times x minus c plus d. So you want this to look like b x minus c. You want it to look like that. So I'm going to factor out the negative x minus 1. And then I've got my plus 4 out here. You see, so this tells me that b equals -1, c equals 1, and d equals 4. So it's this is a horizontal reflection. C equals 1 is a shift right. So say shift right. And D equals +4 is a shift up. Okay? So let's sketch our little picture. Like so. The endpoint is going to get shifted 1 to the right and 4 up. So my endpoint is going to be here at 1, 4. And it's horizontally reflected, so instead of drawing it this way, it's going to be reflected horizontally and go that way. Let's make that nice smooth curve. And so that's my square root curve, like so. And so now we'll fill out the information it asks. We'll say, where is the endpoint? Well, we just labeled it. It's at 1, 4. And remember, we just get those through recalling our parent function transformations. Our domain, well, this function is going towards the left, towards -infinity. So this is -infinity up to, it's going to continue and then stop right here at 1. So that's going to be 1 bracket. Our range, don't be deceived, our range is at 4 going up. Yeah? So our range is bracket 4, and the function continues upward. So let's try and describe the end behavior here. End behavior. Okay, I did a little underline. And again, this is as x approaches the right versus as x approaches the left. So I'll say as x approaches. You know, that little arrow means approaches, as it's going to where? Well, on the right, it hard stops at 1. So as x approaches 1, y, where is that going? It's going to 4. You see, if I trace along, let's say this is my function, right? If I trace along this function, I'm going to the right towards 1, y starts to go down and then stops at 4. Okay. Then if I'm going left, I say as x approaches negative infinity. You see, because that's as it goes to the left. And where is y going? Y is going up. And there's no real limit here, so y approaches positive infinity. That's my end behavior. Okay. Nice. And by the way, this is true mastery. This is a lot of abstract thinking. You have to be able to picture this function in your head and figure out, its basic features. It's, the core features of this graph without really having a graph. So it's true understanding of our functions here. All right. Next one is a cube root. So the 1/2 is a vertical compression. The +3 is a shift left. And the -3 is a shift down. I didn't use arrows this time. I actually read out the words. So let's sketch our picture. It's shifted left 3, so say 1, 2, 3, and down 3, 1, 2, 3. So that isn't an endpoint because it's a cube root. It's an inflection point. And I know that the parent function for cube root looks something like this. So at this inflection point, since it's not vertically or horizontally reflected, the right leg needs to curve up like this, and the left leg needs to curve down like this. Okay? Give a nice curvature there. Much as I can, at least. Cool. Okay. And so that's the sketch of our function. So we don't have an endpoint, we have an inflection point, which, to remind you, is where the curvature, or more academically we might say concavity, of the graph changes. So you can say, you see how this is scooped upwards here, and then this part is scooped downwards? Well, the inflection point is where that sort of scooping of the graph changes. This is a very big idea in calculus. And so if you take calculus, which I hope you all will, that'll be one of the things you find. Okay, so there's my inflection point. Let's do domain and range. And now, thankfully, domain and range, that's easy money. Domain for cube roots is all real numbers. And this is true so long as you don't choose to restrict it. You can take the cube root of any real number and get a real number. It'll be fine. There's no limitations here. You see, with square roots, you can't take the square roots of negatives. That's why there's an endpoint. But for both your domain and range, for a cube root, you have all real numbers, unless otherwise specified. Okay? If I wanted to limit this in some way, perhaps I could. But if we're just talking about the function as it is, as it stands right there, it's all real numbers, and any shift, stretch, or reflection is not going to change that fact. Now we'll describe the end behavior. And you'll want to be a little bit careful with this because with regards to the end behavior for cube, you might be tempted to say, oh, as x goes to positive infinity, y goes to positive infinity, and so forth. But you have to be careful with if there's any reflecting. So notice, I gotta say, as x goes to the right, and it goes to the right towards infinity because there's no endpoint, then where is y going? Y is going up towards infinity. Again, what I like to do is drag my pencil to the right and then just read vertically, right? As I go to the right, is this graph going up? Is it staying the same? Or is it going down? Or is it approaching some value, right? But as I go to the right, it goes up forever. So y approaches infinity. Similarly, as x goes to negative infinity, as it approaches the left direction, y goes down to negative infinity. And that's my end behavior. Move on to the next one, the last one here. These take a while to explain, but if you truly have a good understanding of this, you can do this very, very fast. Okay, so this is a vertical reflection, and this is a shift right. So again, I will sketch my function. 1, 2, 3, 4, 5, 6, 7, 8. Put our little point here. And it's a vertical reflection, meaning our function is not going to look like this, because this piece is going to be reflected downwards here, and this piece is going to be reflected upwards here. And that's kind of challenging to conceptualize. So the lower leg on the right looks something like this, and the upper leg looks something like that. I'll try to make that a little bit more smooth if I can. Okay? All right. And so that's the end behavior of, or that's my curvature of the graph. So where is my inflection point? Well, it's only shifted right 8. So it moves 8, but the y value stays at 0. And your domain, well, that's, like we've said, that's all real numbers. And so is your range. Again, any shift, stretch, or reflect is not going to change that fact. Finally, our end behavior. As x goes to infinity, notice y goes down this time, right? On the previous graph, as x goes right, y goes up. But on this graph, as x goes right, y goes down. So as x approaches positive infinity, y approaches negative infinity. And as x approaches negative infinity, y goes upwards towards positive infinity. And there you have it. There's 4 graphs nicely sketched. Just a quick sketch to get an idea of the function. I was talking to the calculus teacher the other day, and she was telling me that the students who are most successful on the AP Calculus exam, whether you're taking BC Calc or AB Calc, the students who are most successful are the ones who can very quickly identify the key characteristics of a graph given an equation. The students who can do this skill of just sketching a function and figuring out its key characteristics, she said that it comes into play very, very handy in calculus. And those students are usually the most successful. So that was just her words. So thought I'd share that with you. Okay, moving on to 15. We've got some more complicated simplifying expressions. And so none of this is new or different. It's just harder. It's just more. That's all. Okay? So let's go through these. I'll probably alternate colors here. So working through letter A, the goal is to simplify. And notice it does say You can do it in radical form or using rational exponents. It doesn't really matter. I just want you to get the practice of simplifying. So, what I like to do with multiplication of roots is I'm going to use the property that root AB equals root A times root B. And also, multiplication is commutative, meaning A times B times C is the same as B times A times C. It's the same as C times A times B. It does not matter how the order in which you multiply, because multiplication is, as we call, commutative. So, all of this stuff, well, all of it could go under its own root, like so, right? I could say 2x cubed times 6y, right, and so forth. I could say all that. And you know what? Maybe for the notes, I'll write that. This is equivalent to making the square root of 2x cubed times 6xy squared times 15y. But I would just jump to this step. Put your constants together under one root. 2 times 6 times 15. Then put your variables and just separate them. Square root of x cubed times x and square root of y squared times y. You see, I've basically separated every variable and constant all into their own individual roots. This way I can break down the problem and analyze it sort of piece by piece instead of looking at every single thing all at once. Now, 2 times 6 times 15, think smarter, not harder. Don't actually multiply 2 times 6 to get 12 and multiply that times 15. You're looking for perfect squares, so what I would do is factor this. 2 times 6 is 2 times 3, and 15 is 3 times 5. So you have two perfect squares here, 4 and 9. And you can take the square root of 4 and 9, and that's 2 and 3 times square root 5. Then I've got times the square root of x to the power of 4 by just adding the exponents times y to the power of 3 under this radical. Now square root x to the 4th, that's just, that's just x to the 4 over 2. So it's x squared. And then y to the power of 3 is y to the 3 halves. So I could say this. But I'd like to simplify. I'm just going to go with radical form and not rational exponents. I just put that there in case you wanted to do that way. But I'm just going to go straight up radical form. So this will be 6 root 5 times x squared times, notice this is y to the 2 halves plus 1 half. So I don't want to take up too much space here doing that. Look, here's what I'll do. Y to the 3 halves equals y to the 2 halves plus 1 half, which equals y to the 1 times y to the half, which equals y square root y. Yeah? Although, do be careful here, because y to the 2 over 2 is taking the square root, so you got to put your absolute values here. So this is really times y, absolute value y, root y. And so this finalizes, let's put all the stuff underneath the square root together and leave everything on the other outside together. So 6x squared times absolute value y square root 5y. That is our result. Like so. Okay? So just see how I broke that piece by piece to address all of that. Okay? All right, let's do letter B now. And for letter B, I'm going to use a very similar idea, but I'm just going to use the division property rather than the multiplication. So this, the square root of a over b, is the square root of a over the square root of b. So you could put all of this under its own cube root, okay? You could say cube root of 108 x to the 12th over 4x to the 5th y squared, or y to the power of 6, okay? And, well, I guess there's multiple approaches. We could just simplify the expression inside the radical first and then just apply the cube root. And I think I'm going to go with that approach because I like that better. Or you could split this into three different things, like cube root 108 over 4 times cube root x12 over x5 times cube root 1 over y to the 6th. Which do you like more? Do you like this approach? Or do you prefer what I was saying about simplifying the thing inside? I have so many decisions to make. You know what? I'm going to go with this approach that I just wrote. So I'm going to write that a little bit neater, okay? So I'm going to rewrite this equals cube root of 108 over 4 times cube root of x to the 12th over x to the 5 times cube root of 1 over y to the 6th. By the way, you don't have to do it this way. But I think I'm going to go with this approach because you can see me work each individual piece a little bit more clear than if I were just doing it all together. So 108 divided by 4, let's see, what is that? 27? Oh, wow. Ha! Wow, that's just beautiful, isn't it? Cube root of 27. Oh, that's just perfect. Times cube root of, well, let's use the, you see I've got 12 x's on top and 5 x's on bottom. That means I have 7 x's in the numerator because 5 of those cancel. And then times cube root of, let's call this y to the negative 6. Why not? Yeah? Okay. And so now I'll split this up. Cube root of 27, that's thankfully just 3 times, this will be x to the 7/3 if I'm using rational exponents, times y to the negative 6 over 3. I'm just using the rational exponents to accomplish that. And real quick to show you, x to the 7/3, this is how I simplify this. That's x to the 6/3 plus 1/3, which is x to the 6/3 times x to the 1/3, which is just x squared times cube root x. So this becomes 3x squared times cube root x times y to the negative 2, power of negative 2. Okay, so I should probably put the y squared in the denominator now because I don't actually want the negative exponents, meaning the numerator will be, this equals 3x squared cube root x over y squared. And that is my answer. Nice and fully simplified. Simplify as simplified as it can be. Okay? If you left it as y to the power of negative 2, that's fine. It's just as valid. But I would probably use the expression like this. Okay. Letter C. Maybe I'll do this one in blue as well. Oh, oops, sorry. Where am I? Okay. Actually, this one's not that bad. So this one uses a property. You see, if I have AB to the n, that equals A to the n times B to the n. That's one of my properties. So I can just kind of apply that 1/2 to all of these powers. This is like x to the 5th to the 1/2 times y squared to the 1/2 times z to the 1/2. And then I'll just use the property that you can multiply exponents, right? A to the m to the n equals a to the mn. So this is x to the 5/2 times y to the 2 times 1/2 is 1. Careful here, you are square rooting that square, so that needs to be absolute value y. And then this is, well, just z to the 1/2. Now, again, I'm going to split this x to the 5/2 as x to the 4/2 plus 1/2, which is just x squared times x to the 1/2, which equals x squared root x. So this equals x squared root x times absolute value y times square root of z. And I'll put those under the same square root. So I'll say that this is x squared absolute value y square root x times z. And that is fully simplified, like so. Okay? All right. Nice. Last one is D. Oh boy, look at those negative exponents, would you? Okay. So let's first apply the power. Again, I'm also going to use. I'm going to use. It's actually. This is going to use a combination of both of those two rules. So the numerator is going to be x to the 1/3 to the -3, and then the y to the -3, over x to the 1/2 y to the -2. And then I'll just apply that -3 exponent onto the x one, so it's x to the -1/3 times, x to the 1/3 times -3, y to the -1/3, over x to the 1/2 y to the -2, which equals x to the -1 y -3 over x to the 1/2 y to the -2. Now, you could just subtract the exponents from here, and that would be fine. I kind of like to just flip them when I can. That's just a me thing. What you could do is say x to the -1 minus 1/2 and y to the -3 minus 2. Careful, okay, because it's not minus 2, it's minus -2, which is plus 2. That's kind of why I like to avoid that. So I'm going to rewrite this. Everything in the numerator that has a negative exponent goes in the denominator. Everything in the denominator has a negative exponent goes in the numerator. So on top, it'll be y squared. On bottom, it'll be x to the 1/2 times x to the 1 times y cubed. Now, x to the 1/2 times x to the 1, we're going to add those exponents. And then there's 2 y's on top, 3 y's on bottom, so it'll be 1 over x to the 3/2 times y. And okay, maybe you could leave it like this, but x to the 3/2 is x to the 2/2 plus 1/2, which again is x to the 1 times x to the 1/2. And that's absolute value x, okay? So I could say that this is equal to 1 over absolute value x square root x times y. Considering what I wrote in yellow over here, it's absolute value x root x. But if you want to rationalize the denominator, which maybe we do, I'll multiply by root x over root x, giving me, but then you have absolute value x times x. Okay. Root x over absolute value x times y. Well, if we square it, we would be okay. Right? If x was like -1, no, we would not be okay. So we'll leave it like that. Yeah, I think we have to. Yeah. I think we have to leave it like that. I didn't think about this ahead of time. I would say, personally, this is an okay. This is an okay answer. I might say that. Just because when you rationalize the denominator like that, that's kind of, ugly. You've made it look a little bit uglier. And what I was thinking inside my head, sorry, I'm just explaining this. I was thinking, could absolute value x times x, could we make that x squared? No, you couldn't. Because if x was, say, -2, then you'd have absolute value -2 times -2. That's -4, but -2 squared would be +4, which is not true. So we actually cannot combine those. All right. And then that's that page. So, woohoo. Wow, that looks so pretty. Look at all that. I like my color coding. Oh, it looks nice. That last one's kind of icky, though. D sucks. I'll tell you this. A lot of times, these problems, they'll say something like, assume x and y are positive, meaning you don't have to worry about the absolute value business, and that would make it look a little bit prettier without those absolute value signs. So sometimes we do that. We don't even want to deal with the negatives. We just want to look at the simplified expressions. Okay. Last page, and these are on solving. Okay. These are very important. 16 and 17. Oh, yeah, I would definitely practice these before the exam. Questions like this will be on your test. So, just because they're in the mastery section doesn't mean they're not fair game. Okay? So, let's do number 16. The basic premise, let me say the steps. Basic steps. 1, isolate radical. And 2, raise to reciprocal power. Then solve. Because that's essentially all you do with these problems. You get, if you have like x to the 2/3, you get that alone, and then you can raise that to the 3/2, so it comes out nice and pretty. Okay? So I'll start by adding 3. I'll say this is equal to 1/2 x minus 40 to the 2/3 equals 18. Zoom in here for you. Then I'll multiply both sides by 2. Notice, look, you could use the reciprocal power at this step, and it would be okay. It's just that if you did, you'd have to make sure you put 1/2 to the power of 3/2. And that's just just move it over and make your life a little bit easier, okay? Just do this and say that 18 times 2 is 36. Okay? It'll just trust me. Makes it much easier if you just completely isolate that. Okay? Now, we'll raise to the reciprocal power. So I'll say this is going to get raised to the 3/2. And over here, it's going to be raised to the 3/2. Now, keep in mind, when you raise it to the 3/2, you're taking a square root. I'm going to say raised to 3/2 means taking square root. Oops, don't need the x. So I must have plus or minus. Okay? Because I've told you again and again in class, whenever you take a square root as an operation, there's always two possible outcomes, positive or negative. We don't know which, so we have to test our answers to re-verify it. Okay, so this is like plus or minus 36 to the 3/2. Now we can interpret 36 to the 3/2 as plus or minus square root 36 to the power of 3. So square root of 36 is 6, so that's plus or minus 6 cubed, and 6 cubed is 216. So this is plus or minus 216. So if I come over here, I could say whoop, boop, like this. Oh, I didn't want to curve like that. Thank you. Let's do right this. That's better. Thank you. So x minus 40 equals positive 216 or negative 216. So I'll say this, or x minus 40 equals negative 216. And if I add 40 to both sides, boop, boop, then here x equals 256, or x equals, oh boy, what is that? Negative 260. I don't want to do the math in my head. Can I just use a calculator? Hold on. I'm trying to do it in my head. I don't like doing this. 16 and 24. So what's 200 minus 24? Is 80, 76? 176? Negative 176? Anybody? Negative 176. I'm going to double check that. I don't trust myself. Oh, I should have. I should have trusted myself. I was fine. Okay. So those are my two answers, but I need to check. Check for extraneous. And because this problem is a little complicated and it has ugly answers. Well, they're not ugly, but they're hard to do mental math with. I'll just use a calculator. This is why you are allowed a calculator on this part of the exam. So let's store 256 for x and punch in that equation there. So clear 256 stores for x, enter, and I believe it's 1/2 times, was it x minus 40 to the power of 2/3. Oops. 2/3. And then I think it was a plus 3. And we wanted to know if this equals 15. Oh, I got 21. Let me make sure I did that right. Oh, it's minus 3. Hee hee. Hold on. Can we copy that down? Let's try that again. Minus 3. There we go. Ah, okay, it is 15. Hooray. So the first one checks out. Check. Do that in gold. Check. And then we'll just do the same thing with negative 176. So x stores for negative 176. Enter. Hello? Oh, I'm sorry. Negative 176. Clear. Negative 176. Oh my God. Stores for x. Enter. And then I'll enter this again. Oh, it also equals 15. So both work. Both work. Therefore, x equals brackets 256 and negative 176. Both are true. And done. Beautiful. That's not that bad. Okay. The reason this one's tricky to remember is having that plus or minus when you take the square root. I think most of us could solve this one no problem, but it's the plus or minus. You might miss the second answer if you're not careful. Okay? All right. Let's solve the next one here. As I said in one of the other videos, you can isolate either radical and square it, or we'll raise it to the reciprocal power, and that'll work. But it's usually better or less complicated, meaning you'll save yourself some messy algebra if you isolate the more complicated radical. So like I would call this one simple, and I would call this one more complicated because the other one has a plus 24 with it. Now, you could square both sides. You can't. You absolutely can. And the result won't be that bad. It's just, I think it will be a little bit easier if we rearrange this as square root. We'll add this to the other side. And then we'll do 12 minus root x. I think if you do that, it's going to be a little bit prettier to work with. But it's okay. You don't have to. All right? You don't have to. Okay. So I square away that square root. This becomes x plus 24 on the left side. On the right side, it's 12 minus root x times itself. Okay? And so we have to use the distributive property here. That's 12 times 12 is 144. Then minus 12 root x. Then minus another 12 root x. And then a double negative is positive root x squared. So really, I could rewrite this as x squared minus 24 root x plus 144. Oh, I'm sorry. Root x squared is not x squared. It's just x. I messed that up. Yeah. Root x quantity squared, that's just x. That's not x squared. I made that mistake. Okay? So this equals x plus 24. So if I subtract, here's what I'll do. I'll show you. Subtract x from both sides. Those cancel out. And then I'll also subtract 144 from both sides. Just so you can kind of see that. So then 24 minus 144, I think that's negative 120. Should be. And that equals negative 24 root x. And so now divide both sides by negative 24. I'm assuming that's positive 5 equals root x, and then I'll just square both sides. So 25 equals x. Yeah? Here, just so you see it. 5 squared equals root x squared. Therefore, x equals 25. And did you check for extraneous? Okay. Here's what I'm going to do. So say x equals 25. Let's check. Check. So the check says square root of x equals 12 minus root x plus 24, and we're testing 25. So does the square root of 25 equal 12 minus square root 25 plus 24? Well, that it says 5 equals 12 minus square root. That's 49. So that says 5 equals 12 minus 7. True. Yeah? True. So I'll finalize it as therefore x equals 25. See how I just checked this one by hand? I didn't have to use a calculator. Sometimes it's just faster to do it that way. Okay? And by the way, if you're ever truly unsure, maybe you're scared you missed an answer here, if you have the app for Desmos, you can just always type in the left side of the equation and then the right side of the equation, and it'll create two graphs. And notice these only have one point of intersection at 25, 5. So x is 25. And that's true. There it is. Okay. All right. One more for the video, and we are finished. So, solve the equation below. Check for extraneous solutions. Let's do it. Now, I don't think I'll throw something this complicated on the test, but it's still good practice, okay? Still good practice. I'll isolate the radical, the more complicated one, as I might say, onto one side. So this is now root 6x plus 2 on the other side. Okay? Now I'll square both sides. 12 plus 2x squared equals root 6x plus 2 squared. So this is now 12 plus 2x equals, root 6x plus 2 times itself. Okay, so you get 12 plus 2x equals root 6 times root 6. That's just 6x. And then plus 2 of those, and then another 2, that's 4 root 6x. And then it's plus 4 here. Okay? Now, I move everything to one side, so I will subtract 6x from both sides. And I'll also subtract 4 from both sides. This gets me 8 minus 4x equals 4 root 6x. And then I'll divide by 4, yielding 8 over 4 is 2 minus 4 over 4 is 1, so it's 2 minus x equals root 6x. And now you can square both sides again. So you see, we isolated one radical squared, and then we still have a radical, so we have to isolate again, square again. And so when you do 2 minus x times 2 minus x, this equals 6x. Now this is 4 minus 2x plus x squared equals 6x. So let's rearrange that. Okay, it'll be x squared minus 4x plus 4 equals 6x. Then I will subtract 6x from both sides. And I just need a little bit of space. I don't need to go too far up. I guess I could. Like that? Sure, why not? I hate that arrow. Try that again, Mr. Spake. Boop. Okay. So this will be x squared minus 10x plus 4 equals 0. And is that factorable? I don't think so. So, is this quadratic formula? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So this equals x equals 10 plus or minus root, that's 100 minus 16 all over 2, which equals 10 plus or minus root 84 over 2. 84, well, let's look at that. Let's simplify that, huh? Root 84. Oh, sorry, I'm holding my iPad wonky. Let's do that. Let's root 84. Well, that's root 4 times 21. So that's 2 root 21. And 21 is 7 times 3, which both of those are product of prime numbers, so I can't reduce that any further. So this is 10 plus or minus 2 root 21 over 2, meaning x equals 5 plus or minus root 21. And I do that by dividing that by 2. Now check using calculator. Because you have two answers here. 5 plus root 21, 5 minus root 21. Okay? So, we're going to clear this. So, 5 plus square root of 21. We're going to store that for x. And then, what was our equation? Root 12 plus 2x. So, square root 12 plus 2x minus root 6x. So minus square root 6x. And we want this to come out to positive 2. Ooh, negative 2. Okay, so let's do 5 minus square root 21 and store that for x. And I'll copy this. We want this to come out to positive 2. Good. Okay. So only one of them works, and that is the 5 minus option. So we noticed 5 plus root 21 is extraneous. Therefore, x equals 5 minus root 21. Okay? So let's try that. 5 root 21. Box it and call it a day. That's your answer. It's one answer, okay? It's not 5 and negative root 21. It's 5 minus root 21. That, whatever that number is, that's your answer. Again, you can verify this in Desmos if you'd like. What did we say? It was square root 12x plus 2. Was it 12x or 12 plus 2x? Okay. Plus 2x plus square root 6x. And we wanted to see where this was y equals 2. But that's not right, is it? Oh, it was minus. I see. Minus. Okay. And it seems like, so 0.417, and when I do 5 minus square root 21, hey, look at that, 0.417. Yep, and that's the only time that graph hits that line, so we are done. And I might say quad erat demonstratum, or whatever, however you say it, QED. We are finished. That which has been demonstrated. Okay, I'm mathed out for now. I love my math, but I need to go enjoy the rest of my Monday. So, I hope this video was helpful. I hope you had fun with it, most importantly. And take care. I'll see you later. And you guys are going to do great on our test, yeah? All right. Bye-bye.